In this video tutorial, we're going to show how to check punching shear for two-way slabs, and this could be either an RC slab or a PT slab. We're going to demonstrate and define the process for checking punching shear, and we're going to define the different inputs that the user can make relative to the check. This includes some new features that are found in version 2019. So we'll go ahead now, and we're going to be using a PT slab here. This is a single level slab. It's actually occurring on plane 2 of a multi-story structure. So to check punching shear, we can do this various ways. We could actually develop the check based on a global solution of an entire structure, or we can go to a single level and just run that particular level in isolation to check punching. So the first thing we want to do, obviously, is to model the slab, load the model, and we'll assume that that's been done on the user's side. If we review the load combinations, we're going to go over here to combinations. We're only designing punching shear for strength combinations. So we can see this particular model has a couple of strength combinations defined. These are gravity only combos. If the user wanted to incorporate lateral plus gravity, they could always develop additional combinations that included both. But here we just have self-weight, dead load, live load, and the hyperstatic load case from the PT that's included in these two strength combos. Under floor design, we're going to go over here to shear design, and we'll talk about the inputs here for the design for two-way slab criteria. So for shear design options, we have the ability to design using studs or stirrups. And the methodology is actually outlined in our documentation relative to the program. Also, technical note 504 contains detailed information on equations and expressions used to design for two-way shear. If you're interested in that document, you can always contact support@adaptsoft.com to obtain that. We're going to be using studs. We'll use 1/2-inch diameter studs. Now the default here is 2 rails per side. And let me go ahead and do a quick sketch of what we're referring to. So clearly, if we have a square column, maybe this is a 12-inch column, or a 10-inch column, 2 rails per side may be sufficient. So this, in other words, this is somewhat restrictive relative to the requirement per code, where the spacing between these can be no more than 2 times the effective depth. There's an option, if we look down here, that's by default selected. It says limit the rail spacing to 2 times the effective depth. So what that means is that if we have a column that's a long rectangular column, where in reality we actually might need maybe 4 or 5 rails on one side and maybe 3 on the other, 2 per side isn't going to cut it. It's just not going to work for the design. So using this option, the program fills in this space so that it meets the 2 times effective depth requirement. And we could have unequal number of rails per side. In this case, we have a 3-5 configuration. This becomes applicable when we look at the output for the design. So that's what this particular input does. It's somewhat related to this. If we deselect this, then the program will only design for 2 rails per side for any column in the structure. Okay, we have a few other selections here. We can extend the critical section to the slab edge. And if we look at a couple of conditions, we're going to take a look at this column, and we're going to look at this corner column. The program will categorize the columns under basically 3 or 4 conditions. One is an interior condition, where you have basically a 4-sided critical section within the reinforced zone. The other is a corner condition, where we have a free edge, and I'm going to change the color here. This is now our critical section here. The question is, this is the true free edge, and this is what we'll call a virtualized free edge here. So if this distance between the edge of slab and the face of column is less than 4 times the thickness of the slab, the program discounts this. It says this is a corner condition. If this is also less than 4 times the slab thickness, this becomes a 2-sided critical section, where we have side 1 and 2. And the program assumes that the free edge by default occurs at the back side of the column, or the face of the column. So we have this we'll call this B1 and we'll call this B2. Clearly we have length of critical section beyond that virtualized length. So this is somewhat conservative. If you want to take advantage of this leg here, I'll call this A and I'll call this B, then we could use this option to extend the critical section to the slab edge. By default, this is turned off. Again, conservatively, if you turn it on, you'll see differences in the amount of reinforcement and the stress checks. They should go down and somewhat soften the check in a way, as well as the amount of reinforcement needed. The same condition could occur for, this is a corner condition. This might be, for example, an interior condition, four-sided, and this is a end edge condition here. I'll call it E/E. This condition is treated similar to the corner, where we have a free edge. We might have a slab or a column here, and the program looks in this direction. This is less than 4 times h. This direction is not, nor is this direction. So now we have the virtualized edge of the slab here, and this becomes our 3-sided critical section. And then as we move out away from the reinforced zone, we start to check this least critical section, B0 as we call it, away from the D/2, away from the edge of the reinforcement. So this is how the end edge condition is treated. We'll have direct shear force, plus we might have bending this way and bending this way, and that determines, what the properties are of this critical section relative to the direction of bending for the contribution of shear due to the moment. And this free edge, if we wanted to treat this leg and this leg, again A and B, then we can turn on this option here, extend critical section. There's also this option for providing uniform spacing of studs. Now in legacy look at the program and the way this was treated in previous versions, 2017 and prior, if we have a column and we need studs on these rails on the column, the program would always treat these in terms of sections, or what we call layers. So the program would check layer 1, which is D/2, layer 2, which is again D/2 from the previous layer, and so on. And between each layer, we determine what is the requirement of studs here. This is for L1. What's the requirement studs in this gap, D/2 in spacing. This might be L2, L3, and so you might get variances in the then the number of studs and the spacing between layers, just depending on rounding and the program's mechanism for designing the studs within each layer. And that might lead into a design where you need, maybe studs spaced at 2 inches, and then 2.25, and then 2.25, and then maybe 2 again, depending on rounding. So this is a very specific outcome of the reinforcement. It's just per computation. Well, if you have spacing that varies, let's say you have a rail that's 48 inches long, and you have spacing that varies from 2 to, let's say, 4 inches in the different zones along that rail path relative to these layers that we develop, the program, when we take the uniform spacing, is simply going to take the total distance from here to here. We'll call this L, length of the rail, L sub R, and it divides that length of rail by the minimum spacing. So we'll take that over 2, and that gives us uniform number of studs at the minimum spacing. So again, this is a conservative output. If you compare the difference between turning this off and on, you're going to see you're going to bump up the number of studs in order to uniformly space those pieces of reinforcement on the length of the rail. The next option here is to consider the critical section outside the shear reinforced zone. And in ACI, this is specific to ACI 318 version 14 in terms of the requirement that this is tackling. When we reinforce a column for punching shear, we make sure that at d over 2 from the outside of the reinforced zone, we use the least critical section. And when we have configuration of reinforcement like so, that least critical section would be in this octagonal shape. So this was required in code references in 3.18.14 to use this critical section. Now, if we had reinforcement off of a diagonal, obviously this changes the critical section. Then our least critical section looks something like this. So it's rectilinear versus octagonally shaped. In the 2019 version of the program, this particular option, when selected, the program will check critical sections. Let me go back, and I'm going to draw this again. So it will check critical sections based on a rectilinear shape. Each critical section, again, is called a layer. So you might have, for example, 10 layers checked at distances d over 2 from the previous layer. We continue to check those section shapes until there's no reinforcement required. That is to say that the actual shear stress is less than the allowable shear stress provided by the concrete. At that point, when no additional reinforcement is required, we'll call this here, we'll call this layer 10. We will actually recheck layer 10 at its exact position, but what we do is we simply cut off this leg and this leg, and we base this now on an octagonal shape. So we recheck this section, again at d over 2 from face of column. That's at this layer based on the rectilinear shapes. When there's no reinforcement required, this is at a distance d over 2 from the previous section, which would be layer 9, which required reinforcement. So this is the first critical section not requiring reinforcement. We come back and we check it with this reduced critical area. And if we need reinforcement, we continue to check this. If that stress, rather, is greater than the allowable 2 squared of f prime c, then we basically come back and we recheck another octagonally shaped section. We keep growing those section shapes out until we limit the stress to less than or equal to 2 squared of f prime c. And that's what this option here is for. This checks those octagonal shaped sections beyond the location where the initial rectilinear shapes require no reinforcement. So if you compare an outcome of reinforcement between having this off and on, you're going to get more reinforcement likely due to this particular check by reducing the critical section shape. So that's what this was introduced in 2019, a new option in 2019. It actually applies to all ACI design codes except for the 99 code in the program. What is meant by that is that if you select ACI 99, this actually would not be enabled. This would be grayed out. Any other ACI code selected in the program from criteria design code would allow you to select this. And this edge distance right here, if I blow this up, here's our column, here's our rail. This edge distance is really just the distance from this edge to the center line of the stud. Okay, so that's what this is defined as. That helps us calculate this distance here, this distance on the diagonal. And finally, there's one additional check that's included in version 2019. That's this application of minimum reinforcement for drift. Again, this is relative to ACI 318. There's a requirement that when you have a two-way slab with two-way shear reinforcement, you have to meet some minimum allowable stress within 4 times h from the face of the support. When this is checked, the program supplies the design with that particular reinforcement. If you look deeper into the technical note referenced earlier, that gives the requirement there in that technical note. So we'll go ahead now. We're just going to leave the defaults here as they are. I'm going to analyze. I need to make sure I mesh the slab first. So we'll mesh this. And after we mesh, we're going to execute the analysis. I'm just going to execute this for the strength combinations. Okay, once that's done, the screen looks a little messy, so I can go to visibility and just say go back to my default display. And once we've analyzed, we can come back to floor design and just execute the shear check. So that's done. The question now is, well, how do we get results? There's two sets of results. There's graphical results, and then there's our tabular results. So let's now go. I'm first going to determine which combination do I want to select the results for. Do I want to isolate one of the strength combos or just use an envelope of strength? I'll use envelope of strength. And notice that if we have service combinations or any other combination type other than strength, and we select that here, when we go over here to analysis and look at the punching shear results, these will be inactive. You can't select them because it only applies to strength level combinations. So keep that in mind. We'll select envelope of strength. I have 4 different graphical checks. The first is stress check. This tells me that there's at least one column that doesn't meet stress check allowable, meaning it could either be exceeding the code allowable maximum stress or it needs reinforcement. And we can see we have 2 conditions that actually apply in that case. We have multiple columns that require reinforcement, all of our columns, and we have one over here. This is a corner condition that exceeds code. So we're going to take a look at one of these interior conditions further when we get into results. The question is, when we exceed code, what does that mean? Does the program still add reinforcement? And the answer to that is no. If I jump down over here to reinforcement, you can see the program provides all columns that are reinforceable with kind of an abstract graphical view of the reinforcement, and I'll define how that's to be interpreted here in a moment. But this column is just left alone. If we go back to stress check, it exceeds code. We don't add reinforcement for it. We can go into the details further related to that column in terms of the analysis and the design results and kind of determine why it's failing, and that gives us a little bit of information as to maybe we need to add a drop cap or a drop panel to thicken up and beefen up that location to pass the stress check for two-way shear. So we have stress check. We can go to stress ratio. This particular instance, we're checking moments separately. We can combine the stress or we can check them separate. By default, we have this set to design for moments each side separately. The code is silent on that. There's some literature that does cite why we might want to check the stresses separately. So we give the option here for the user. We just happen to run it with the default. And this just gives us the worst case stress ratio for each direction. So this is the direct shear plus the shear induced by the moment for each bending direction. And this is not obviously comprehensive, or we might have 30 entries here. This is worst case. And we do have some Excel output that would summarize each and every individual layer that we check for each column. The condition just gives an indication of the actual condition that's being checked for the column. You can see these colors are somewhat muted because we have this gray on top of it. So I'm going to select that and just say hide that selection. Oops, let me try that one more time. Okay, and if I come back to this, the colors brighten up a bit, and it's easier to kind of correlate here with this legend. So most of these, the interior columns are obviously four-sided, they're interior. This just gives an indication of the critical section shape that we're using at d/2 from face of column. This does not necessarily indicate every critical section shape, especially when we have the check made for the octagonal shape. You'll notice here, and what this check really is more intended for is to show that at end edge and at corner conditions, the free edge of the column is assumed away from the actual physical edge of the slab. So if I was to go back and change this to extend critical section, we would see that these dashed lines on the side would actually extend out. Those would be updated if we come back and retoggle this selection. Finally, if we go over here to reinforcement, this gives us an indication of the reinforcement. And what this means, we have a legend here, so I recommend the user follow that legend. This kind of tells how this is spelled out. So if we take a look at this column right here, this tells us that we have 12 rails total. There are 3 rails per side necessary to meet the 2 times D distance between rails in a peripheral row of reinforcement. So this number is total rails. 3 and 3 means we have 3 rails in the R direction. The local axis for the column is this is R, this is S. If we double click on the column and we look at the releases, that would show us that schematic. But just in short, this is R direction, S direction, where we have 3 rails located in the R direction and 3 rails located in the S direction. Because it's in interior condition, we show arrows that are scaled to this distance in all 4 directions. That means we have rails on all 4 sides. So we have 3, 3, 3, and 3. We have a total of 12. And the spacing of studs on the rails is 5 at 3, 7 at 1.5. And so that spacing for a 1/2 inch diameter stud equals a total rail length of 25.2 with D/2 from face of column at the first line of reinforcement. Okay, that's how this can be interpreted for the outcome of the reinforcement. Now if I come back, let's say this is 12 total studs. If I come back to shear design and I say use uniform, and I go back and I execute this again, okay, and I redo the reinforcement here, you can see I now have 17 total studs at 1.5. So it grew from 12 to 5 studs within the same length. It's just we have a total length that we divide by the minimum requirement that bumps us up to 12. So this is uniform spacing versus the non-uniform spacing of reinforcement. If we wanted to get a schedule or a pseudo schedule of this output, we could go here to reports, punching shear reinforcement, and this would then give us this schedule. This is the envelope of strength for each column. So each column would be uniquely identified in this schedule. If we come back, let me go back to the option here. I'm going to take uniform spacing off and rerun this. And I'll go back to reports, punching shear. Okay, once I use the non-uniform spacing, then this report comes quite a bit larger. This is actually the legacy report that we produced in version 17 and behind 17. So this identifies again each column, but it also identifies every unique combination as well, plus the envelope. And now we have the number of studs per rail, number of rails, and the spacing for each group along the length of the rail. So this is 2 at 3, 4 at 3, 2 and 1.5. So this becomes a bit more extensive in terms of the reporting when you have non-uniform spacing, because each column under each load combination condition provides potentially a unique layout of studs, which again can then be enveloped here in the final block of this report. There's a couple of other reports. There's a stress check results report. This just gives a quick overview of the worst case condition. So this will identify the column label, the condition of the column, and then it identifies the forces used to check the shear, the two-way shear at that column for the given combination, and stresses versus allowables. So this again only produces information for the worst case condition, whatever produces the worst allowable stress or the stress ratio. You can also do the same for parameters. So this would identify critical section lengths and effective depth and so on. Okay, and finally, if we go back to the reports tab and under the punching shear, we can go to this Excel file, punching shear report, and this gives us basically data and information for every particular section. So we can see if we go back to our model here and we pull up this column that we were checking earlier. This is column number 6, and coming back to the report here, ID 6. This was checked for 10 critical sections. This is the geometry of each critical section, effective depth, the design lengths in both directions, the design area, We have section constants and so on for the different critical sections. This is just the percentage factor, let's say, for contribution due to moment for the shear. And then we get into stress checks at each one of those sections and so on. So this is a stress check, for example, for column 6 under both combinations. We have 10 layers checked for the strength dead and live, and then 7 layers checked for strength dead only. So this gives us stresses for every independent section, reinforcement required for each section, envelope of reinforcement, and then ultimately the schedule of reinforcement for each column. So this gives you more detailed information for each layer, whereas the reports that we see here really just give this for the worst or the most critical of the different layers that are checked for the column. And then ultimately, again, if we wanted to export any of this data to a CAD file, we could use this export to DWG. This doesn't obviously give us the layout of reinforcement or a detailed drawing of the reinforcement, but it's more abstract in nature and would have to be somehow synthesized down to how you represent your two-way shear reinforcement in plans or on schedules. If you have any questions, please contact us at support@adaptsoft.com. Thank you.